Hello. So we're going to do section 2.4 and bear with me here. This is the third time I've made this video, but the first time using this app that I'm using now. So here we go. Now before we go on, I want to show you a couple sites in case you don't have your calculator with you. I figure the most annoying thing to do on your calculator, or when you don't have your calculator, is to do RF. So you can see here on this site, which I'll put on my site for you to go to. You can choose the rows and the columns and then enter your matrix and then hit submit, and it'll give you the RF form of the matrix. And then this other one here is kind of similar. You just enter everything there. You see calculate RF. It'll even show the steps for you if you're trying to do it by hand. But you don't really need to show the steps if you're just looking for the answer. All right, so here we go with section 2.4. All right. So in this section here, you're going to do something called partitioning a matrix. So when you have a matrix, like you see this matrix right here, this is a 3x4 matrix that's told you right there. And so when you partition a matrix, let me mention, you can print out these notes before, or you could just watch and listen, or you could jot some things down as you go if your printer doesn't work. But anyway, the PDFs will be up there for you to look at on Blackboard or the website. So here we go. So 3x4 matrix. So these little lines right here are just little things that partition the matrix, kind of like when we used to do augmented matrices. Anyway, you can see that this first one, that's one way to partition it. And what you have here is now you have one matrix, another matrix, another matrix, and another matrix. So you have four matrices that you have partitioned this into. So you see you can have four matrices over here. And then the next little thing is another way to do it. Maybe somebody broke it up by all of its rows. And so you can see row 1, row 2, row 3 that they called it. And so you have three matrices. Each one of them is a 1x4. All right, and then this one is done by columns. So it's no big deal. It's just, you don't have to partition them yourself. But remember, back when we watched that video of the lady kind of introducing linear algebra, she talked about you have huge data sets, and so sometimes you want to partition them into so that certain areas kind of stay together and you can see them and how they're acting with their other areas. And so that's how you use partitioning. All right, so when you partition a matrix, so we're looking down here, example 1. So notice that this was a 3x6 matrix, and so there were 12 entries and it got partitioned up. So notice you have 1, 2, 3, 4, 5, 6 pieces right here. So what you've done is you've partitioned this into a 2x3 partitioned matrix. So you have 2 rows of matrices and 3 columns of matrices. And so when somebody gives you this name here, A13, that means they want, in this matrix, they want the first row, third column, they want the matrix in that spot. So that would be right here. So A13 is the matrix 6, 4. Okay. All right, what are the dimensions of A22? So A22, so that would be second row, second column. So that's a sky right here. So that's the matrix 3, 1. So A22 has a dimension of 1 row, 2 columns. So it's a 1x2 matrix. Okay. All right, so now the next part right here. Addition and scalar multiplication. So of course, when you do scalar multiplication, you can multiply everything by a scalar. That doesn't change. And then with the addition of matrices, you just have to make sure that, if somebody's going to ask you to add, they have to all be the same size. And so not only does your original have to be the same size, like the last one was a, a 3x6, but it has to be partitioned the same way also. All right. And so there's going to be some wording that they're going to tell you that when somebody says to you down here, when somebody would say to you, our partitions are conformable for block multiplication, or up here, never mind, I guess it doesn't do it for addition. Anyway, so to add, they have to be the same size. When you multiply, you have to have the sizes the correct way. Remember when you multiply, like if you do a 3 by 2 and you're trying to multiply it by, it has to be a 2 by something. So, you know, these things have to match. So when somebody tells you it's conformable for multiplication, that means everything works out. So I'm going to show you one of the multiplications on the next page. So let's go to that. So here's an example of two matrices that were partitioned. And so when you multiply these, it's easier if you were going to kind of break them up or kind of number them or put, I'm not going to number them, but I'm going to put letters here. So I'm going to label this one A, B, C, and D. So you have those four matrices in that spot. Then you have matrix E and F. All right, so when you have this first matrix right here, this is a 2 by 2, and we are multiplying it by a 2 by 1. Now remember, we're looking at the big portions, like the blocks that are the sizes there. So a 2 by 2 times a 2 by 1 is going to make a 2 by 1 again. So that means we're going to have an answer matrix with two matrices, 2 rows and 1 column. So I'm going to partition it. So it's going to pretty much look like this guy right here almost. All right, so let's take a look. So when I multiply these things, remember I'm going to be multiplying AB, so all this part right here, times EF, all that part right there. So when I do that, I need to kind of write out what's happening here. I'm going to be multiplying AB times EF, and when I do that with multiplication, then I basically multiply A times E and B times F and add those together. So right up here in the spot right there is going to be A, E plus B, F. All right, and then this spot down here is going to be this little piece here, my CD, again, times my EF. So I have CE plus DF. All right, so when I do that, I'm going to need some calculations. So of course you can put some of these things into your calculator, but basically I'm just going to do them by hand right now. So I need AE. So A times E, so I'm going to be multiplying A times E. So remember, I'm doing my row times my column. So it's just normal multiplication. So I have 1, 2, 3 being multiplied by negative 1, 3, 0. So that row times the column. And this is a 2 by 3 multiplied by a 3 by 2. So that is going to be a 2 by 2 matrix. All right, so 1, 2, 3 times negative 3, 1, 0. That'll be negative 1 plus 6 plus nothing. So that'll be 5. And then keep going, the same thing. I get 24 the same way, and then 10 and 18. All right, and then I also need BF. All right, so BF, so I got this guy times that piece right there. So I'd have a 2 by 2 times a 2 by 2, so I get a 2 by 2. So negative 1, 0 times 1, 2, I would get negative 1. Then I'd have negative 1, 0 times 0, negative 3, so that gets me a 0. And then keep going the same way, I would get a 4 and a negative 9. So remember, I have to add these together. And so that's going to go up top here. So 5 and negative 1 add up to 4. And then 24 and 0, so 24. And then 10 and negative 1, so 9. And then 18 and 0, 10, wait a minute. 10 and 4, sorry about that. 10 and 4, 14. And then 18 and negative 9, so 9. Whoopsie. Oh. All right, so now I have to do CE and DF. So I need CE. All right, so CE, so that would mean I'd have to do this guy times this guy. So that is a 1 by 3 times a 3 by 2. So that will end up with a 1 by 2 matrix. So 1 row, 2 columns. So 0, 5, 2 times negative 1, 3, 0 gets me 0, 15, and 0. So I get a 15. And then 0, 5, 2 times negative 2, 4, 6 gets me 0 plus 20 plus 12, so 32. All right, and in much the same way, I'm going to do df. So I got this times this now. So remember it has to be the same size as what CE to add those together, but I have a 1 by 2 times a 2 by 2, so I will get a 1 by 2. So you do that multiplication for df and you get 1, 0. So remember I have to add these together, so 15 plus 1 is 16, and let's see, 32 plus 0 is 32. So there is your solution to this multiplication. All right, so on to the next example. Now in the next couple problems here, example 3 and 4, we're just going to basically, it's just like a, I don't know, kind of like a theoretical multiplication that we're doing right here. And so they tell you, first of all, that it is conformably or partitioned conformally, so we can do multiplication. But there are a couple new things in here in both of these. You see here in this first matrix, you have this 0 appearing, and over here you have both 0 and this I appearing. So when you see those things, the O, that is the 0 matrix. So it's just a matrix with all zeros. So when you multiply anything by this, you just get 0. And then you have I, that is your identity matrix. So identity matrix means, like, if you multiply matrix A by I, you get A back again. So it's like multiplying by 1 in a way. Remember, the identity matrix is a matrix with 1s all down the column and the diagonal, and then everywhere else is zeros. So when you multiply this by anything that the sizes would fit, you get the same matrix that you started with back again. All right, so we're just going to go do our regular multiplication here. So here we go. I have a 2 by 2 and a 2 by 2, so I'm going to get a 2 by 2. So I have EO times AC. So E times A is EA, and then O times C is 0, so I'm just going to get EA. Then I have EO times BD. So EB is just going to be itself, and then O times D is 0 times D, which is 0. So I have EB. All right, now in the bottom section there, I have OF times AC. So 0 times A is 0, and then I have F times C. So that's FC. Oopsie. All right, and then I have OF, or 0F times BD, so that'd be 0 times B, which is 0, and F times D. So I have F and D. All right, so on the next one, example 4, so I have the identity matrix coming into play, and again, a 2 by 2 times a 2 by 2 is a 2 by 2. So make this one a little bit wider here because there's going to be some addition that doesn't go away to 0. All right, so I have I0 times AC. So I times A is A again, and 0 times C is 0, so I'm just going to get a big old A right here. Then I have I0 times BD. So again, same idea, I get B. Now in this next little portion, for the second row, I have negative x times A, which is just negative x times A, and then I have plus I times C. Well, that would just be C. So I'm going to get negative XA plus C for that spot. And then the last part, I have negative x times B plus I times D, so it'd be negative XB plus D. So let me see if I write that again. Negative XB plus D. All right, so that's the best I can do. All right, so the only difference in example 5 and 6 is that now they've given us an answer and they want us to do something a little bit different. So in this problem right here, it says find formulas for x, y, and z in terms of A, B, and C. So for each of these problems, I want to come up with a formula. I want to say that x equals something, y equals something, and then z equals something. I'm coming up with a formula for these things. So I got x equals, y equals, and z equals. So let's see if we can do that down below. All right, so my multiplication. So now it's different because I have an answer. So I have xo times ab equals the identity matrix. So what I get from that is that x times a plus 0 times C, so 0C equals the identity matrix. So I don't really need that 0C because it's just 0. So I'm going to get rid of that and just say it equals identity matrix. Well, oh my gosh. So when something equals identity matrix, then they multiply, that means they must be inverses of each other. So x and a are inverses of each other. Therefore, I can gain from this that x equals a negative 1. So that x is the inverse of a and vice versa. So now I have a formula for x. So that would be a negative 1. All right, so let's keep going with our multiplication, see what else happens. I have xo times oc equals 0. So that's true. It doesn't really produce anything for me. I have yz times ab equals 0. So let's write that down. Y times a plus z times b equals 0. We'll deal with that a little bit later. And the last little spot right here, I have yz times oc equals I. So y times o is nothing. Then I get z times c equals I. So it's the same thing I had earlier. So I know that z and c are inverses of each other. So z is c negative 1. So the inverse of that. So z is c negative 1. All right, so let's look at this guy right here. So I have answers for x and z, and then I need an answer for y. So I'm going to use this information right there. So I have now that ya, I'm going to put the zb on the other side. So make it negative, I'm just subtracting. So minus, and then zb. Okay, so remember I want all a, b's, and c's on this side right here. So I'm going to replace that z because I know that this was true. So I have ya equals negative. Z is replaceable with c negative 1. And then I have b. All right, and then I'm basically going to, the way you can't divide by a, so you can't divide with matrices, but you can multiply by its inverse. So I'm going to go ahead and multiply both sides by the inverse of a. So y equals negative c negative 1 times b times a negative 1. Now it's debatable where that a negative 1 goes because of the sizing, so you would have to see if it should go in front or in back, but there's your formula. So negative c negative 1, b, and a negative 1, inverse of a. All right, so let's do this for example 6 and see how it goes. So I have ab times xo, so that'd be a times x equals I, so ax equals I. So there I go. So x is a negative 1, just like we learned earlier. Let's see. ab times y0 equals 0. So ab times y0, that means a times y equals 0. So a times y equals 0. So from this, you know, a right here has an inverse. That's what the first one told me. So if x is the inverse of a, that means a has an inverse, so the a matrix can't be 0. So when you tell me a times y makes 0 and I know a can't be 0, that must mean that y is 0. All right, let's see what the next part tells me. So I got ab times zi equals 0. So that would be a z plus bi, so basically plus b equals 0. All right, so let's see if I even need the second row here. Let's see what this one tells me. So I already learned that y was 0. That doesn't do anything for me. I learned that x, so let's see, I could do this. I just need a formula for z, so I can say that az equals negative b if I just move it over by subtraction. And then I think I can just say z equals negative b times a negative 1. Or, you know, again, because of the sizing, we might have to reverse this, but negative b times a negative 1. And there we go. So all we're looking for is formulas for x, y, and z. Alrighty. So on to the last page. The last page is just like a definition in a way. So when something is called a block upper triangular matrix, so when a triangular matrix is when you have basically you're going to see later in this chapter, like let's say you have numbers here, like not 0, here, 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 but, and then every place else has numbers, but then let's say you had zeros all right here. I forget how many rows and columns I was doing. But anyway, when you're like your lower half is all zeros and your upper corner is all items, that's called an upper triangular matrix. And then when it's the other way around, it's called a lower triangular matrix. And so a block diagonal matrix is when you just have matrices along the diagonal and you got zeros everywhere else. So there's just some definitions. You don't really need to do much with them right now, but it says a block diagonal matrix is a partition matrix with 0 blocks off the main diagonal. And such a matrix is invertible if and only if each block on the diagonal is invertible. So it's just like a little definition and rule. All right, so one last page to show you, and that is your homework. So for section 2.4, these were most of the problems listed on your green page that I gave you earlier this year on the cardstock. And then, so I want you to just whittle it down to just these 5 problems, and then also do this multiplication problem right here, just to practice with that a little bit. And I'll talk to you soon. Bye-bye.